I wrote down the last statement on the preceding carelessly. The condition here is that fx is less than 0 and that the slope is decreasing, which would mean that fxx is what drives this thing toward the decrease, and fyy is what drives us toward a decrease in this direction. It's not that fx is negative, it's that fx starts out at 0 and decreases, giving us a greater and greater negative slope. And similarly in the y direction, not that fy is negative, fy starts at 0 and it's close to 0 throughout a small interval, but that it has a tendency to curve downward, so that the tendency of the graph to turn downward in this direction and this direction can be balanced by the tendency of the graph to turn upward when we move in this direction. If the upward curvature as we move in this direction is large enough compared to the upward curvature we get from the curvature in the x direction and the curvature in the y direction, the net result of those curvatures, then the function will tend to increase in this direction, decrease in these directions. If fxy, or which is equal to fyx, is big enough compared to the combined effects, and let's say combined effects of fxx and fyy, then we can have the saddle point, and we will in fact have the saddle point. The combined effect of fxx and fyy is measured by fxx times fyy. The effect of fxy is measured by what? Well, we're getting to multiply fxx by fyy. Now, it's not a matter of fairness, but we can kind of think, if we're going to be fair about this, that we better let fxy multiply itself. Again, when we get to the epsilons and deltas, we'll see why it's so, but the effect of fxy is then going to be measured by fxy squared, multiplying fxy by itself, so that this term basically has the same order as this term. This allows a comparison between the tendency of curvature to change the function as we move in this and this direction, and the tendency for the curvature to drive the change in the function as we move in this direction. Our test to see whether we have a maximum, a minimum, or a saddle point at a critical point then, and remember, critical point is what occurs if fx and fy are both 0 at a point. We define the discriminant to be fxx times fyy minus fxy squared. Now, in the present example, the example we've been considering here, fxx is less than 0, and fyy, bad y there, but is less than 0. So fxx fyy is greater than 0. Now, fxy squared is greater than 0, so that negative fxy squared is less than 0. So we have, in this case, something that's greater than 0, something that's less than 0. Now, our hand-waving argument that we've been using here indicates that if fxy is big enough, then it can counter the effect of fxx and fyy. So if fxy is large, then fxy squared is bigger than fxx fyy, so that the discriminant is going to be negative. Because if this is bigger than this, when we subtract it from this, we're going to get a negative. And we've seen that when fxy is big enough, that's going to lead us to a saddle point. So this turns out to be, now we haven't proved this at all, we've simply asserted it, that this d less than 0 is the condition for having a saddle point. We'll look at some different cases here in a minute.